Okay, right now I'm going to discuss energy in simple harmonic motion. Now, I probably should have included this in my first video with simple harmonic motion, but we're just going to cover it right now. So when we're talking about energy, there's a few things that we should discuss first. This energy in simple harmonic motion works pretty much exactly the same way it works in all other motion, which is why sometimes I feel like, do I really need to discuss it? But at the same time, there is some interesting, I guess, kinks to it that I personally find really fun, and it's also probably one of my favorite parts of simple harmonic motion. Now, when we're talking about this, you're going to mostly be applying outside knowledge. There's not much to really learn, but there's going to be some like basic information about energy that you're going to want to know. Well, the main thing that I'd say is just the shape of a graph for simple harmonic motion. So with simple harmonic motion, what we're doing is let's use the most basic example. We have a spring, and right now it's at its most stretched state. So that means at this state right here, it has all potential energy. So if we were to make the energy for this right now, let's say this is K and this is U. Now you should make this better than what I'm making it look like if you're like on an actual test, but that's besides the point. It doesn't matter right now. Then right now we have an energy of U. But let me see if I can do if I know how to do this works. Right. Let's say instead it's over here. Now it's not stretched at all anymore. And all of its energy is going to be back into K. And next, what's going to happen is, do I got this. Let's go. Pages. Control V. Oh. Now let's say it stretches or it gets compressed all the way down. So its distance from equilibrium is again the same number. We're just going to say it's A like A. And now all of a sudden, all the energy is back in the form of U. And it's just going to repeat this cycle. So it's going to go from here, and then it's going to go back into this at this state, where it's all K, and then go back here, where it's back in U, the starting state. And it's just going to repeat this on cycle. The graph of it should end up looking something like, if we're talking like the total energy. And I'll just make this be the potential energy, something like this. While the kinetic energy should look something like this. And the energy should at all points add up to the same amount. Where this is whoops. Let's just quickly. Okay, pretend that's a straight line. Perfectly horizontally flat straight line. That's basically all we really need to know. The rest of it just comes down to logical thinking and applying what you already know about things like energy and momentum. So let's do some actual problem solving for practice. And this is going to be some mostly algebraic work. Not going to work with many specifics. Let's say, okay, so we have a mass spring system, horizontal one. We compress it all the way down, and so it's compressed all the way here in equilibrium. This distance A, we're just gonna say A, because that's the typical value that we use in this class. And now it's going to be bouncing back and forth, back and forth, back and forth. But it's now this is just path of its motion. Now let's say we drop another block on top of here and falls down. And we're going to assume that there's no friction between this block and the table, by the way. We're typically going to assume stuff like that. And this block falls, it lands on here. And this box of, equal mass, so identical blocks, and they stick. So they stick on each other. And now what happens to its motion? First off, does the A value change? Its amplitude, the distance it travels. The answer is no. The amplitude is not going to change. It's still going to go all the way from here, back to here, back to here, and back. Now, does its max speed change? Don't you think of this for a second? Okay, the answer is yes, the speed does change. Now, why? Well, the max energy in the system is still exactly the same. We're still going to have the same max energy of whatchamacallit, I'm just gonna say max energy. We don't really need a specific value. Adding this mass isn't gonna change it because at this point it's all potential energy. That's not changing anything. So that means 1/2 mv squared equals E, where equals E max. And this value does not change, but m increases. So that means V has to decrease. Now let's think about this more specifically now. By what factor does V decrease if we dropped, a block of equal mass onto this one? I'll let you think about that. Okay. So we have 1/2 mv squared equals 1/2 m2 v2 squared. And then we can just say mv squared equals 2m times v2 squared. And so what we end up getting there is v squared over 2 equals v2 squared. Now just take the square root of both sides, and you end up getting that v2 is equal to v over square root 2. This is just one way you can use energy. Let's try another one. Okay, let's try this. So we have a block in it. I'm not even gonna draw a specific image, but we have a block and attached to a spring. I've drawn this 100 times and I'm still just as bad drawing it, so I'm not gonna do it some more. We have a block attached to a spring, we compress it, and now it's going all the way back and forth, bouncing around in standard simple harmonic motion. It has a 6-second period, okay? Very long period. And it has a total energy of E, okay? So E is its total energy. No, wait, I believe there's a text feature that I can use. Yeah, so E is the total energy. What is its kinetic energy at t equals 1 second? I'll let you think about that for a quick second. After 5 seconds, if you need more time, well, you're probably going to need more time. But if you don't, that's good. But if you do, just pause it, and I'm going to move on to the explanation. Okay. Oh, I forgot to write the... Oh, well. I'm just going to quickly write the question right here. What is the kinetic energy in terms of E when t equals 1 second assuming the spring mass system starts at state of highest compression. I'll give another 5 seconds. Okay. I'm gonna start explaining. So, we're at t equals 1 second starts at its state of highest compression. So, let's say for this one, at least when I solved it first, I drew a circle. This is 360 degrees. And what we know is its motion is going to basically almost like follow the path of the circle, with like sinusoidal functions. Specifically, we know is start most compressed, and that means we can use things like x equals a cosine of omega t. That's something that we can use. And that also means that the v is equal to minus a omega sine omega t. So let's quickly just get back to the circle. So if we're at t equals 1 seconds, then that means we're 1/6 of the way through the period. And an angular period, or I guess I'll say angular period. I'm going to rephrase that. The total degrees for a period, like a period is when it's traveled through all 360 of these degrees. So 1/6 the way through that. That means you've traveled through 60 degrees. So that means we can plug in 60 degrees into this sine omega of t. And actually, we don't need to do that. We can just plug this in for this a cosine of omega t. And if you know your unit circle, which I do expect you to know, but if you don't, you can just use your calculator for this. Cosine of 60 degrees. This will give you 1/2, I believe, right? Yeah. I'm just going to double check that with calculator next to me. Yep. So that means that its position is currently we're at halfway through the position, and something that we know is that spring energy is 1/2 kx squared, where x is the position. So we're halfway through the position, halfway through the total position. So that means this x can be swapped with, we'll just use a because that's a standard value, a over 2, to represent to the a max. And what we know is 1/2 ka squared equals e. If we have a over 2, that means this is 1/2 k a squared over 4, because we're plugging a over 2 in for this x now. And so that you'll notice that this is this number divided by 4. So that means the potential energy at this point is equal to E over 4. So the U is equal to E over 4. So that means that the K is equal to 3E over 4 due to the energy being constant. That's probably one of my personal favorite questions. Okay, let me see if I want to do another one on this list. Okay, this one I think is a nice one. So, we have an object and it's oscillating, okay? It's also part of a mass spring system. I'm not going to draw it again because I'm not good at drawing. And the block, we're going to use specific numbers this time. The block is 2 kilograms, and it has a period for like its oscillation of 2 seconds. So I'll just say equals 2 kg, t equals 2s, and I know what we know is it's that it's 0.3 meters from equilibrium. It has a speed of 0.5. And we're being asked, what is the amplitude of the block's motion? So basically, how far does it travel from equilibrium? What's its max position from equilibrium? So how do we go about this one? I'll give you guys a second to think about this one before we move on. Okay. So what we know is that this block is a mass spring system. So we can begin first by setting up for its period. So we know that t equals 2 seconds, and we also know that t equals 2 pi over omega, and therefore omega equals 2 pi over t. So we can say that omega equals the square root of k over m. So we get that the square root of k over m equals 2 pi over t. And what we know is that this is equal to just pi, because we got that t equals 2. To get that the square root of k, we can plug in 2 for m, for 2, is equal to pi. So that means we know this. And we can actually just quickly expand this. We get k over 2 is equal to pi squared, or k is equal to 2 pi squared. And we can also just use the basic equation that 1/2 kx squared plus 1/2 of mv squared equals 1/2 ka squared, where a is the maximum position away, so like the maximum distance. It's the amplitude. And we know this because energy is constant throughout the time. This value is the maximum energy because this is at its most compressed state, and all of its energy is just going to be in potential energy. Here is going to be for the rest of the time. Well, we can actually use this for all times. It's just that when it's at its most compression and stretched states, this value is just going to be a, and this value is going to be 0. And when it's at its point of equilibrium, this is going to be 0, and this is going to be at its peak. That's a pretty relevant detail, though. So what we can do, we can be blah, 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 blah. I can talk. What we can begin doing here now is plugging in values. So first, let's just plug in 2 pi squared for the k. So we get that 1/2 times 2 pi squared times the x, which is 0.3. So because that's squared, that's 0.09, I believe. Yeah. It's that block there. And this one is 1/2 mv, so that becomes 1/2 times 2 times this is mv squared times 0.5. So that's 0.25 then. So that means we get that the total energy is equal to, I'm just going to draw this line to help organize this. We get is that 1/2. Actually, we can simplify this now. This 1/2 and 2 cancel out, so we get that 0.09 pi squared plus 0.25 equals, and we can also plug in this value in for this k here. So we just get that a squared pi squared. So yeah. And now it's just a matter of solving this algebraically. Just divide both sides by pi squared and then take the square root of this side of both sides, and then boom, you have that. You should get that a is about 0.34. So that means the amplitude of the blast motion is 0.34 meters. Okay. I think those are the main questions I want to solve. Let me see if there's anything else I want to do. Okay, that one's kind of unnecessary. Okay, yeah, I think I'm going to call it there. The rest of this is really just applying what you already know about energy and concepts of motion. So if you can just go review things like basic energy, then you should probably be fine, including things like interpreting graphs. Anyways, thank you guys for watching. I hope you guys better understand energy in simple harmonic motion now. Yeah, see you guys next time.